last talk for the conference is Oliver, who works at Bloomberg, and is going to tell us all about embedded Python. Please make him welcome.
All right. My name's Oliver Rue. I'm a software engineer at Bloomberg in New York City, and I'm here today to talk to you about how to build robust embedded systems. Whether you want to build better home automation or the next Mars rover, hopefully what we discussed today should help you build resilient software wherever it runs. To get started, we should probably try to better understand what an embedded system actually is. Formal definitions of embedded systems will say something like this: a microprocessor system built to perform a dedicated function. That's a good definition and still very applicable. But for the purposes of this talk, I actually like this comment on a Reddit thread regarding the definition of embedded systems. Vidicon31 says, "I feel like it kind of depends on who you ask, but I would say that an embedded system is a device that contains a computer that the average person would not consider being a computer." In this case, a computer would be a general purpose system built to perform a range of different functions. And by this logic, an embedded system is anything that the average person, probably no one in this audience, would not consider one of these. So a microwave is not a computer. A car is not a computer. And a thermostat is not a computer. And in the past, internally, each of these things would likely look quite different from a computer as well. They'd probably run on some constrained microcontroller or microprocessor, and might only ever run one version of software, usually called firmware, for that reason. But today, things have changed. The internet is everywhere now, and compute power is laughably cheap. So now we have the Internet of Things. Our cars are lousy with touchscreens, and you can play Doom on your smart fridge. While still not operated like a computer, internally, many of today's embedded devices look a lot more like your PC. Your smartwatch, smart refrigerator, or smart thermostat are likely running an operating system very similar to your laptop or server. And if you run Linux, they might be the same. These sorts of embedded devices, the ones running a modern OS on modern hardware, are what I want to discuss today. Because these devices are not operated like modern computers, but have modern computers at their core, building and deploying them introduces a bunch of interesting hardware and software problems. So let's talk about a couple of them. Regardless of the device, it will need to be powered in some way. And the first issue we run into power is availability. Anyone who's dealt with a flaky smart device will know that the number one way to fix it is simply to turn it off and on again. However, modern operating systems don't always appreciate unexpected power loss. And even if the OS is okay, your software may not handle that well either. Power consumption is another problem. Many embedded systems run on batteries, but even modest embedded CPUs can draw significant amounts of power. And it's even a good idea for wall-powered devices to think about power consumption. Our smart home devices might only draw a couple watts, but they run all day long for years, which can quickly add up. Now let's talk about the basic building blocks of a modern computer system: CPU, RAM, and disk, also known as persistent or non-volatile storage. Modern operating systems are great at abstracting away the physical details of the underlying machine. However, while your code might appear to run the same on embedded hardware, you can quickly run into issues if you expect the same performance as your typical desktop or server. Other than limited resources, CPU and RAM should be fairly transparent to the embedded programmer, but non-volatile storage can take specific considerations. More often than not, an embedded OS is using some form of flash memory for its non-volatile storage. And as you may know, flash memory has a finite number of write cycles. So while it may not appear different from the OS's perspective, over the life of the device, the storage can wear out and cause issues. This is especially relevant when the device is expected to run for years or decades and never had a lot of storage to begin with. Now let's talk failure. While power cycling a device may be the easiest way to reset it, that doesn't scale well. Instead, embedded software should be written in a fault-tolerant manner, always considering how to fail gracefully in every situation. Furthermore, the operating system must be properly configured to handle failure in your application. And if a device requires external connectivity, like Wi-Fi, Ethernet, or Bluetooth, there are additional failure modes to consider as well. While the low-level details of these protocols are likely taken care of by the OS, any connectivity can be very unstable, and our device needs to handle connection loss gracefully and predictably. You may be thinking that these are good considerations when developing software for any environment, and you're right, but they become even more critical when developing for an embedded system. If your device is inaccessible, either because of its location, physical enclosure, or even software security, a simple software failure could effectively brick the device. And when there is an inevitable failure in your system, detection and debugging can be much more troublesome in an embedded environment. Logs for a desktop and cloud applications are often available in some form of logging console. But for a number of reasons, like connectivity, data usage, and storage, accessing logs in an embedded system can be much more difficult. We also must thoughtfully consider how our devices represent their current state to users, because they likely have limited methods of communication. Beyond operation, your device likely requires specific configuration. Wi-Fi passwords, IP addresses, host names, application config, and much more are need to be loaded onto the device for it to operate. We take for granted how easy this is on our PCs. But an embedded device likely doesn't have the luxury of a monitor, keyboard, or mouse. It might not be located in an easily accessible place. And this process becomes even more cumbersome if you're managing a fleet of devices or if your configuration needs to change over time. Another huge configuration consideration is security. Embedded devices share all the same security concerns as other computer systems, but the risk can be exacerbated by poor or lacking configuration. There have been numerous well-publicized examples of embedded devices being compromised by old security vulnerabilities or just default passwords. On top of that, physically remote devices are easier for bad actors to access and can put your data at risk. And in the event of a vulnerability, or your software changes, you will need a way to deploy it. Deployment mechanisms for software are already numerous and complex. And if you add on the issues of fault tolerance that we just discussed, this process becomes even more difficult and risky. So now that we've touched on some of the high-level issues with embedded systems, let's go into a bit more detail and discuss some of the strategies to solve them. By no means will this be a comprehensive guide to building reliable embedded systems. By definition, embedded systems are usually designed for a specific function in mind, so every use case will have specific requirements. And this is a good time to mention that the title of my talk is a bit misleading. None of this is specific to Python, and instead it can apply to any software that you choose to run in an embedded environment. Nonetheless, I hope what we discuss gives you some useful insights for your next design. To start, let's talk a little bit more about storage. Before we can talk about solving issues with embedded storage, we need to discuss some of the problems in a little more detail. As mentioned before, the storage in your embedded device will likely be some form of flash memory, like an SD card or eMMC. These devices are great. They're cheap, plentiful, and easy to use, but they also have the tendency to wear out over time if you aren't careful. The best way to avoid this is to thoughtfully consider how and when we write to persistent storage. One great example of this is application logging. We all love to litter print statements throughout our code, but if each print statement ultimately ends up on our small flash storage, we can quickly run into issues. And the same is true for OS logs. This may seem like a simple problem to fix, but even the pros make this mistake. Famously, back in 2021, Tesla had to recall over 100,000 vehicles because their onboard eMMCs were failing. The culprit? It appears significant application logs were just written directly to storage, shortening their lifespan and ultimately causing failure. Another peril with storage, which relates to our issues with power and fault tolerance, is the danger of corruption when the power unexpectedly fails. Flash storage devices are complicated at a low level, and interrupting a flash operation can potentially corrupt a large block of your storage, jeopardizing the device as a whole. If you've used a Raspberry Pi, you may have heard of this before. This issue plagued the Raspberry Pi community for years, causing regular corruption and data loss. And while multiple factors were at play, unexpected power loss, insufficient power supplies, and low-quality SD cards were the main suspects. And beyond low-level hardware, your embedded software needs to handle power loss as well. What if you lose power while in the middle of writing the main config file for your application? Simple problems like this could easily brick your device. There are many solutions for flash storage wear or corruption, but my favorite is to completely avoid disk writes altogether by making my file system read-only. This is likely what many of your embedded devices already do, and this is one reason you can yank the power on your Wi-Fi router and it's no worse for wear. There are many ways to accomplish this, usually depending on your OS and hardware. For example, on the well-known Raspberry Pi, they make this super easy with something called an overlay file system, which is a feature that makes your file system read-only while making it appear writable to applications, except all writes are temporary and are only stored in RAM. And if a full read-only file system is not an option, another good strategy is to send noisy disk writes like OS logs to a temporary RAM-based file system, while writing important, less frequently changing data to persistent storage. Most OSs will make this fairly easy as well. Read-only or RAM-based file systems are great, but this strategy does have its drawbacks. Related to what we discussed about debugging, if you're sending your logs to RAM and your device loses power, all the logs are lost, and that can make it much more difficult to diagnose issues. You should also consider mitigating storage and power loss issues at the application level. One of the best ways to do this is to simply use libraries to handle interruptions for you. When properly configured, file-based databases like SQLite usually include multiple protections against data loss in the case of unexpected interruption. Even simpler, if you want to avoid corruption while modifying files from your application, I usually do something like this. Read the existing file, make your changes, write your new file contents to a temporary file, and finally, rename that temporary file to the original file name. At least on Linux, file renames are generally considered atomic. So if you were to lose power during this operation, on restart, your application would either see the old or the new, but nothing in between. Now let's talk about fault tolerance, a huge topic in itself, and not just relevant to embedded environments. It's always a good idea for us to develop our software to proactively handle any errors it encounters. As always, it's application specific, but here are a couple basic design patterns for you to consider. To start, let's talk about process managers. Because we're concentrating on embedded devices running on an operating system, it will be the operating system's job to start and manage our software processes over time. However, modern operating systems are complex and offer a number of different ways to manage an application. You can use init, systemd, OpenRC, supervisord, Docker Compose, and many others. And your choice is probably application dependent. But my advice would be to just pick one and learn how to use it properly. Don't try to roll your own unless you really know what you're doing. I often pick systemd, mostly because it's what I know and it's available on most of the systems I use. Systemd has a million different options, but most applications can run forever with just a simple config. This config file here tells systemd how and where to start my application, when to start it, and what to do when it fails unexpectedly. With just this, you can enable your service and know that systemd will take care of managing it. Now let's talk about automatic fault recovery. While PCs and servers likely have UIs or consoles to reset them in the case of failure, embedded systems may not share this luxury. One simple pattern that I like to follow is that of a watchdog. In its broadest form, a watchdog is a mechanism that monitors your system for abnormalities and automatically takes corrective action. Often, that monitoring is just checking for responsiveness or connectivity, and the corrective action is a software reset or system restart. It might not be possible for you to foresee every way that your complex software can fail, but if you can find some basic conditions that define the liveness of your software as a whole, you can have a relatively simple watchdog monitor those conditions and reset it if necessary. Now let's talk about fault tolerance and configuration. One of the riskiest times for our devices is during updates or configuration changes. Say you have a remote, inaccessible network device and you need to change its Wi-Fi settings. What if you send the wrong password or the new Wi-Fi network isn't available? For an inaccessible device, this could effectively kill it. When we build configuration mechanisms into our software, it's always a good idea to consider what could happen if you push a bad configuration and either have a fallback mechanism or at least a way to alert on it. There's so many more ways to make you more fault tolerant depending on your needs, and I encourage further research. Regardless of how fault tolerant we make our embedded devices, they will always find new and creative ways to fail. And when this happens, it's important that we have systems in place to monitor and diagnose those issues, let alone ways to fix them. I know for a lot of my home projects, my main technique for monitoring and debugging is simply logging in via SSH and reading the logs. This can be fine for a small number of pet projects on your home network, but it's not advisable or sustainable for anything more than that. Logs and metrics are likely our first instinct when debugging issues with our software. But as we already mentioned, saving logs directly to device storage is not always advisable, and only storing in RAM leaves you blind in the case of power loss. One logical solution to this is just send your logs and metrics somewhere else where they can be safely stored and analyzed. There are numerous good open source options for streaming this data and a ton of cloud-based solutions for collecting and analyzing them, many with generous free tier options. The monitoring solutions we just discussed work well, but they assume the person debugging the issue will get value out of reading low-level application and OS logs. This may not always be the case. I can't think of the last time that I wanted to read the logs on my toaster. Sometimes the best mechanism for communicating system state to a user is through physical feedback. Consider adding displays, lights, or sounds to your device. Something as simple as a single LED can often communicate enough information for a user to diagnose it. Since our embedded systems are computers, but aren't operated like computers, we should always consider more natural ways to interact with users. And finally, let's talk about configuration. At some point in their lives, our embedded devices will need to be configured to perform the function they were designed for. However, configuration can be very complex, and there are a lot of considerations. Single-purpose devices may only need configuration once at birth, And for personal projects, there's nothing wrong with logging in to a device and running an install script. But for anything more, consider some form of automated software image building and provisioning. Not only does this ensure that your devices are configured and deployed consistently, it makes it much easier to scale in the future. There are a couple good options for this, like Buildroot and Yocto, but they're too complex to get into in this talk. Many devices need to be reconfigured throughout their lifetime. And besides pet projects, manually modifying config files is not a realistic option. Instead, we should thoughtfully consider how we provide our users with some form of configuration interface. Sometimes a simple on-device API that exposes common configuration parameters is sufficient, but in other cases, it's better to include some form of user interface. For example, most of our home Wi-Fi routers will present a configuration web UI at a given address that allows us to easily configure device settings in a user-friendly manner. However, there are many more considerations for device configuration that may influence your design, like potential for automation, idempotence, fail-safes, and many more. Beyond application config, our long-running devices may require software and security updates throughout their lives. These mechanisms are usually complex and very closely tied to the OS. The inaccessible nature of embedded devices often exacerbates this, and devices can go years without necessary security fixes. If you're doing small-time embedded work, I suggest choosing one user-friendly ecosystem and following their guidelines. If you're doing large-scale professional work, you may have many more options with varying levels of customization and difficulty. So we've talked about a bunch of problems and solutions for today's embedded systems, but where does that leave us? Today, embedded devices are basically computers, even if we don't treat them like them. They operate much the same as modern computers and face the same challenges, but can carry a greater risk of failure. We discussed a lot of options, but by definition, embedded systems are purpose-built, so each application will be different. However, with thoughtful design, robust patterns, and a bit of paranoia, we can build devices that are resilient, secure, and easy to live with. And by embracing the constraints of embedded systems, we can learn habits that lead to more reliable software, no matter the platform. That's my talk. Thanks for coming.